This weekend I was working on the next lab we'll do. We're just starting extractions, but next up is, we're just starting crystallizations, but we'll start extractions soon. So I was updating this Google slide animation, and it's a monster extraction diagram. So I went with Monsters Inc. theme. Hope you all like it. And today I'll do the intro, and then we'll work on chapter 3. We might finish chapter 3, maybe. We'll see. And as always, you can come to lab and do some work outside of your normal lab time on Mondays and Wednesdays. Today and Wednesday, you could come at like 1:30 and do lab work. You can run an MR or work on an experiment, but just clean up before the 2 p.m. lab starts. And then the same goes for Tuesday, Thursday. There's more of a time frame there, 9 to 10:30. 10:45, I'm sorry, but then clean up before 10:45. All right, so we got a lot of things due, and I want to keep you up to date on them. So exam 1 corrections, that was actually due last week. So turn it in today for partial credit if you haven't already. There's a few of you who haven't turned that in yet. And then determination of unknown structures. So we're coming down to the wire on this one. I set the due date for the actual assignment later than needed. I think it could have been almost due this week, but it's okay. I won't move the due date forward because you might have planned around that. But I did say I wanted you to pre-lab it by today and tomorrow. So that means the pre-lab means to work on it for an hour and a half and tell me how far you get. It might be through most of it, an hour and a half. This one's not too long. And if little or no progress is made, -5 points for the assignment. So trying to encourage you to keep going on the pre-lab and keeping up with the new labs. And determination of unknown structures, the actual full assignment, which you're doing you're giving me the spectra of both spectras of ethyl acetate and toluene fully labeled, and you're giving me the IR of 3 unknowns and the proton and carbon NMRs of 3 unknowns fully labeled. One of those unknowns is yours, 2 are partners. So once you get all your unknowns and everything else, then just turn it in. It's not due till the 18th, but I think some of you will turn it in this week. So it's just nice to get that off the to-do list. Also, the solubility of organic compounds, that's due today and tomorrow, depending on your lab section. So turn that in. I know some of you, especially Tuesday, Thursday, you might not have it done yet. I'll extend the due date more than normal. Usually I say 4 days late and I won't count it against you. I'll add on another 4 to that, but try to see if you can get it done this week. So some of you in Monday, Wednesday lab, I think in Monday, Wednesday, everyone should finish taking data today. And then in Tuesday, Thursday, hopefully most of you can finish on Tuesday. And if not Thursday, I'll be more lenient with the due dates on that one. Got some questions in the chat here. Oh, goodness gracious. Resume share. I paused my share because I had my email up and I didn't want personal stuff to show up. Sorry about that. Thank you for telling me. Please, if I'm doing that, can you just verbally tell me too? That's not your fault at all. It's all my fault. Shoot. Yeah. So here, I'll just back it up real quick. You'd think I would have this figured out by now. I just have to, when I start the Zoom, I have to go spotlight for everyone, record, share screen. But then if I pause screen to check my email, I gotta remember to unpause it. Ugh. So here's the Monsters Inc. extraction diagram I was telling you about. I got a link to it here if you want to check it out early. And then, so yeah, chapter 3, some due dates here. Come into lab early if you want. Exam 1 corrections. All right. Solubility of organic compounds. Do homework B's due this week too, depending on your lab section, Wednesday or Thursday. And then NMR and IR. Okay, so NMR and IR spectra labeling, that's one of the things that students miss points a lot on assignments that they turn in lab because they just don't label them right. I want you to really understand what's going on and label them specifically. So for the determination of unknown structures and for other assignments, most points are usually lost because people don't label their spectra as well. So to help you with that, I have a quiz, an obvious quiz, one where I give you the quiz prior and the answer key prior, and then you come into lab and do it. So do you want to have that quiz this week or next week? We can do it Wednesday, Thursday, or we can do it Monday, Tuesday of next week. I'm thinking you're gonna probably vote Monday, Tuesday of next week. If you want, vote on the chat. The quiz is just I have a proton NMR, a carbon NMR, and an IR, and a molecule drawn on it, and you'll like fully label it. Like on the IR, have bonds, have arrows touching the bonds to the signals, and then on the proton and carbon NMR, you'll do the predictions and fill in the table and all that. All right, looks like all votes for Monday, Tuesday. That's fine. Okay, we'll say next week for that. Format. I'm gonna strike through this, can I? I don't know how to do it here. We'll just say. All right. And then the exam 2, it's coming up in a couple weeks on the 20th and 21st, depending on your lab period. And I want you to do well on it. And a lot of times students don't do as well on the second exam. It depends on the student. Sometimes they don't do as well because now it's mostly just OChem. And perhaps on the first exam, they were leaning on their general chem knowledge, and they did well because they had their general chem stuff down well. Other students actually who aren't so good at general chem, they might do a lot better on the second exam because they didn't have to, if their general chem was weak, that hurt them in the first one, but now, yeah, anyways. So, but I want you all to do well. So the key thing is, don't start to study for it in a couple weeks, start studying now. So for example, we went over Newman projections and we did the energy versus torsional angle diagrams. So if you haven't practiced and gotten good at that already, then you're behind on that. And you don't want to save that up to later to study it. So try getting going on that early, come to office hours. Oh, and then so the key is just study now. The new material you get this week, study it this week, learn it this week. Don't save it for later. Otherwise, when you take that exam, it's not going to go well at all because it's just too much to cram. And studying is important. It's how you study too is really important. I want you to become very good studiers. I want you to be able to study in an hour and get as much done as you used to get in 3 hours of study. So one of the best ways to get good at studying is to come to my office hour and or the past peer session with Morgan, because when you're with us, you're right away we're finding little things to fix and to make everything much smoother. So I say like studying with one of us for an hour is like maybe studying with yourself for an hour and a half, 2 hours. So if you can make it to those, come. All right, and then again, let me check the thread here. And then I had a question about our exams comprehensive. The exams are cumulative, meaning they're always building on each other. But each exam focuses on the newest material, but the newest material is pretty much all of the old material as well, like bond line structures. And I don't know, I want, like on exam 2, I won't have a specific sigma and pi bonding diagram question, but you'll need to understand how that pi bonds, how they work and everything too. All right, so let me get back over here. Lastly, I need to finish up the NMR and IR spectra labeling quiz. And the key, I'm updating it. It was PowerPoint, and I had a IR spectrum on there I didn't like. Actually, I'll show you, and now I'm fixing it up, but I'll share it soon. And the chapter homework C, chapter 3 and 4, I'm updating that, and I'll share it soon too, so you can start working on the homework 3 stuff that we're doing now. Here's what the NMR and IR quiz is going to look like, labeling quiz. So So I'll give you a spectrum and a molecule. You'll know the molecule, and then it's all about labeling it. It's not about figuring it out. So you circle your groups, label your signals, and fill in the table. I don't have the predictions on here. I'm gonna add the predictions too. And then yeah, so it's about filling in these tables like this correctly, making comments about them. The same for the proton NMR. So this is the exact quiz you'll get. Well, yeah, this is correct actually. Yeah. And then the IR, I'm updating that now. So don't draw fragments, this kind of thing. So I don't think there's a quiz today, Alina. Which quiz were you thinking of? I don't think I haven't planned any quiz today. Today is the 7th, just a pre-lab check-in lab. Do an hour and a half of that. And then on Wednesday, Thursday, you got homework B, site building. But I'm being lenient on this. Tuesday, Thursday lab had a couple extra days they missed because of the smoke out day, and then when I took Michaela to UC Santa Barbara. All right, so more questions in the chat here. Is there no quiz today? Okay, sounds good. Thank you. You're welcome. Okay. All right, any other questions about the intro? Well, I was going to show you something, my error I had. Oh, that's a good one. So I have my IR here. And this IR spectrum, it's for this molecule, but here it is again. So it's for this molecule, but it's I added it. So I have the molecule, but I did it with the Nujal mole. If you remember what that is, Nujal mole means you take a solid and you dissolve it in this Nujal oil. And the Nujal oil is this big sp3 carbon hydrogen area, but I don't want that in there. I want the one that looks like our spectrometer. So that's why I have, I'm updating it. This is the KBR disk one that looks more like our ATR adapter IR. So it doesn't have that big Nujal oil signal. All right, and then here, since we're here, I'll show you a little bit. Here's our monster extraction diagram we're gonna get to. We got Scully and what Wazowski. So it's got the the review of this stuff. I told you it's gonna stick around, and it's still sticking around, right? And then we're gonna start off with here's another review. And then we're gonna do we're gonna start off with a mixture of 4 compounds. We're gonna separate them all by extractions, where we add like an acid to make the amine water soluble, and then an organic layer of methylene chloride that'll have the other molecules that aren't charged. And we just keep going and going and going. All right. Okay, now back to chapter 3. We did a radical halogenation of an alkane, and we looked at the bromination. Let's look at it again to review real quick. Let's see if the sound will come through on this one. I think it's way better to do it off my computer, actually. initiation. Where'd it go? Okay, here we go. Let's put some music to it. All right, let's review this really quick.
Check this out, bro. What's that, Brohim?
I took OChem and learned more. More reactions than acid base,
Yeah, Professor, and more.
like radical halogenations.
So here we are, our overall brodacious reaction. And we're going to do this a lot. We'll draw reactions out as their overall reaction, where it's just reactants, reagents, products, and not the mechanism. And I don't want you to mix up like this overall reaction with the mechanism. Sometimes in the beginning, students get confused and they try to like draw a mechanism in this overall reaction, but that's not where you draw the mechanism. The mechanism's down below. Like here's where the mechanism is going to start. And this is called a primary bromide because this carbon is a primary carbon. A primary carbon is a carbon that's attached to only one other carbon, directly attached. So this carbon right here that the bromine's on, it's attached to 1, 2, 3 other carbons. So that's a tertiary bromide. So here we go, radical initiation here. Start with no radicals and we end with 2 radicals.
Nice, Brotator Chip.
You're welcome.
That's not all protein shake.
And then propagation step 1 for the primary product here. Where are they going to meet? Halfway, right? So we started with 1 radical bromine and we ended with 1 primary carbon radical. So radical to radical, that's a propagation. It's propagating the radical chain.
I get my props. I'm radical start to finish.
There's prop step 2. So the carbon radical on the reactant side. It was on the product side on prop step 1, huh? And now here we go.
Ooh, that's a lot more. Oh yeah, I'm all about more Teddy Roosevelt.
And then here's prop step 1, the first prop step for the tertiary product. Radical, radical.
Next OChem exam, expect radical halogenations and a whole lot more.
All right, and then terminations. So they don't happen all that much. They happen at the end of the reaction. So most of the reaction is all this propagation 1 and 2. At the very end of the reaction, the concentration of the alkane and the Br2, those concentrations start to drop, and now there's going to be a relatively higher concentration of radicals, so they're more likely to collide. But actually, let me step back 1 step here. So in the beginning of the reaction, you only have light on for a short period of time, and you only make a small amount of radicals. So almost all of your reaction is the alkane and Br2. There's just a little bit of radicals, and that little bit of radicals starts this chain mechanism that you keep making a radical each time, which keeps it going. Towards the end of the reaction, when your alkane's running out and your Br2 is running out, then you just have radicals left over so they can time to brominate. So 2 radicals can come down, come together. Oh, here I can throw in my. I just thought of this. What's the pause recording stop? Live transcript. Let's see if you guys like that. Enable live transcript. Okay. So then we went from 2 radicals, no radicals. Now we're going to do it between 2 alkanes. So you can see if I number and letter these, it really helps to make sure you don't add extra carbons or lose carbons. This is a tricky one. go. Those are just some of many terminations. I could have also done one where I had, maybe I do below. Let me see, do I? No, I don't. I could have done one between a bromine radical and an alkyl radical, but it just make a brominated alkane. All right, so good. Got that reviewed. Now let's draw some more up. Got some questions on the chat. Is there a quiz tomorrow? Okay, no, not that one. Does termination always lead to no radicals? Yes, that's right, Annalise. Thank you, Ryan. And the radicals are what drive the reaction, so the terminations lead you to having terminating the reaction cycle. Actually, I'll draw a nice little diagram of that right now. Let me get my iPad going. Okay. My iPad's not cooperating. Did I lock it? I did not lock it, so I should be rotating. There it is. All right, Monday, 10-4, good buddy. It's October now. Let's look at this. I'll look at a real simple one real quick. So let's go, we'll fluorinate this. We'll go fluorine and light. I'm doing this as the overall reaction here. Ethane, I can get a fluorine on here. In this case, if as far as like monofluoral products, meaning products with just one fluorine, there's only this product just because it's just an ethane with 2 carbons. It doesn't matter which one you put it on. And then you make HF as well. Okay, so let me show you a way to think of this to see the chain reaction part of it. So we start with fluorine, F2, and then light is added to it to cause it to become the fluorine radical. And that gets everything going, right? We need a radical. And this fluorine radical, it reacts with an alkane. So an alkane can come in. This is the alkane carbon, 1 and 2. So as this alkane comes in, it makes another radical, the carbon radical, and it produces hydrofluoric acid. So hopefully you can see that now. You're starting to get good with the mechanism. See, this fluorine is going to come over and take off a hydrogen to make HF, and it's going to make a carbon radical. And then this carbon radical is going to react with F2, and it's going to produce the product, fluoroethane, and also another fluorine radical. Because remember, when this comes in, it meets halfway, adds a fluorine to the carbon, and then makes a fluorine radical. And then the fluorine radical reacts with another ethane and produces another carbon radical, another product. So you can see how like you have your, what we call this reaction, we have like, this is like a feedstock. This is initiation. Actually, let me do this first. This is initiation. This is prop 1, and this is prop 2. And this ethane is a feedstock you can think of. Like that's being fed into the reactant. The reactant is being fed in to make a product. This is a product. And then here the F2 is a feedstock. And here's a product. And all you theoretically need is a single F2 molecule to make the two fluorines. It can only make, the least it can make is two. Once you have that first fluorine, it can make a carbon radical, which makes another fluorine, which makes another carbon, makes another fluorine. So you can see how it's called a radical chain mechanism. This is a very common mechanism. So this, I had a question, is this called a synthesis? It is a synthesis of a fluoroalkane. But yeah, so radical chain mechanism and, oh, and then if you want, you can see how, if we add any other radical, I'll just make it generic, you can get a termination like that. But the termination is not going to happen until the concentration of the feedstocks get low. Once they're low, then these low concentration of fluorine and the alkyl radical, there's low enough to where they don't always run into like a feedstock, they run into each other, and that's when you get termination. Okay, so I hope you like that. It's kind of a cool little diagram, huh? This is this radical mechanism seen in a lot of things. It's seen in our atmosphere, like where, have you heard of chlorofluorocarbons causing problems with our ozone layer? So the chlorofluorocarbons could react in the same way. They become radicals, and then they react with ozone to create oxygen, so the ozone gets a hole in it. And so one fluorocarbon could destroy many ozones because it cycles and cycles and cycles. So that's a problem. But actually, we've done really well with that. That's one of our environmental situations where we've worked on it and we've improved it a lot. So we've taken a lot of the chlorofluorocarbons. I'm saying it right? I feel like I'm saying it wrong. But anyways, we've taken these things out of our production lines, like we don't have them in as propellants and things as much. And so because of that, our ozone hole has been shrinking. It's been getting better. So kids in like Chile and Australia and New Zealand, they don't have to wear sunscreen to school as much and hats to school as much when the when the UV index is really high because of the ozone holes above them. So that's good. Hopefully we can fix some other natural issues up in Earth. Okay, so yeah, me too. So yeah, as far as the UV index goes, I have fair skin, so I have the problem if I don't wear sunscreen or if I'm in the sun too much or don't have shade myself, then I can get sunburned quickly. But then I have the advantage that I can make vitamin D much quicker than those with darker skin. Like my wife's she gets really dark skin. She never has to wear sunscreen. She does occasionally, but she doesn't all that much. But so she takes longer to make vitamin D, but doesn't get sunburned. So there's pluses and minuses, right? All right, so I want to do a reaction coordinate diagram for this one now. Yeah, the ultraviolet light could cause radicals to form in your DNA, and then that DNA could become cancerous. That's the problem. Okay, so let's look back at the one we did before with the, actually, I'm gonna screen capture it. That one, bromination. There we go. Okay. So we're going to do a reaction coordinate diagram for this example. I'm gonna make it a little bit small so I have some more room for it. And so my iPad's not catching up. Come on, buddy. There we go. Okay, so I have my coordinates here, energy, reaction coordinate. All right, so I start off with my BR2, my initiation, at some energy, BR2 down here, and we add light. And is this first step, do you think it's a exothermic or endothermic? So it involves breaking a bond between the bromines. Does it take energy to break bonds or does it release energy to break bonds? Takes energy. So this is going to definitely be endothermic. Boom, right there, right? There we go. And we make the bromine radicals. Okay. And so that's our first step of the mechanism. And then let's do propagation step 1 first, say. So I'm going to add in my next reagent. I need the alkane. And now in this next step, we're going to break a carbon-hydrogen bond, but we're going to make an HBr bond. So is this going to be exothermic or endothermic? What do you guess? Well, if you guess, I'm thinking you're just guessing, which is fine. I don't think you would know just yet because you'd have to know what's a stronger bond, the CH bond that has to be broken or the HBr bond that's forming. So without tablature data of that, how would you know? So let's look at some of that data. Oh, I'll show you where I get this data from too. I'll find it where you can find it. If you go to the chapter 3 outcome outline, there we go. I've got a data table here with this information. So let's look for the carbon to hydrogen. Here, I'll bring this over. Guess I should take on. So if I want to draw the product for this first one, propagation step 1, primary carbon, then I need to look up the energy that's needed to break a CH bond like that. So let's look that up. So I'll draw it out here. What's the bond energy for this? So this is a primary carbon-hydrogen bond. So when I look over at the table, I see this is going to be bond between just 2 hydrogens. This would be a methyl carbon-hydrogen bond. This would be a primary, and this would be a primary. So this is the way you read this table is it's methyl here. Primary, primary. This one's secondary, and this one's tertiary. So you can see both of the primaries are 101 kilocalories per mole. So let's go with kilocalories per mole. We'll call this one, this equals 101 kcals per mole. All right. So the other thing we need to know is the HBr bond. What's its bond energy? Can anyone find it in our table up here? I see hydrogen, I see bromine. What's the bond energy for that? Yep. 87 kcals per mole. So what we're saying there is that it takes, to break an HBr bond, it's 87 kcals per mole, but also when an HBr bond is made, it releases 87 kcals per mole. So in our mechanism, we need to, this first one, let's go, all right, here, prop 1 primary. We break CH, and that costs us, we have to add in 101 kcals per mole. Should I use a small cal? I think it's small. Huh? What are they using this table? Yeah, the small C. Let me make this font smaller. Make it red. Stand out. Okay, so prop 1 primary. To break the CH, we need to add in that much, right? When we make the HBr, it releases 87. So does this look exothermic or endothermic? So we have to add in 101 kcals to pull apart the H. We only get 87 back. What is that, 14? It's an endothermic step. Now, would you have been able to predict that without this table? No. Would I give you this table if you needed to do that? Yeah, I'll give you the table. Okay, so let's draw that one in. I'll put it like right here. Oh, I'll change my color back to black. There we go. So this is my primary product, and I make HBr as well in that step, right? And I haven't been adding in my activation energies. Here we go. Activation energy for the first step. Transition state 1. Activation energy for the second step. Transition state 2. Now, but what about the secondary? So this was when the bromine reacted here at the primary carbon. What about our secondary carbon? Let me do this. I'm gonna duplicate this slide. So I'll have some more room to write on the next slide. So I'll write this. Let me write it. Let me type it. It'll look better. So let me do that. Duplicate. All right, so now this one, delete that. So I can erase all this. I'll fix that. Oh, wait. Yeah, no, I don't want that. Why do I do want that? Okay. There we go. Oh. But now I want to look at the tertiary carbon to hydrogen. So this is the tertiary. So what does it take to break that tertiary carbon to hydrogen? How much energy? Can anyone tell from the table? Here's the tertiary carbon. Ooh, 96.5, right? Sounds like a radio station. 96.5. Playing hits of the 80s and 90s. Okay, so 96.5, it takes less energy to break that. So, but it's still gonna make a HBr the same thing. It's only gonna release 87. So if I changed, I gotta select this guy. So now prop 1 for the tertiary. To break the carbon hydrogen bond, it's only 96.5 this time. It's still 87 released. So it's is it exo or endo? Still endo. All right, it's endo, but it's less endo, huh? So I draw it like this. It's going to be lower in energy, HBr. And my curve, I'm going to draw it a different color. It's going to look more like this. Transition state to, I'll say transition state to tertiary. Ugh. Tertiary. All right. And so it's got less activation energy too, huh? All right. Then to do the final step, to make our main products, I'm not going to have the terminations on this diagram. They're not really needed and they don't even occur that much. Then final steps are propagation step 2 for the primary and propagation step 2 for the tertiary. So both of those are going to require the addition of Br2. So we need to add in another Br2. So let's see, another Br2 needed here. Another Br2 needed here. And this step is going to be exothermic and exothermic overall. So, and they both come out about the same energy, the final products. We can do the math on them. I'll do it after I draw it. Let's see. Yeah, I should be accurate with it. I'll be accurate with it. Let me just finish this off real quick. So for this step, I need to break a Br2. I'll take the let me select this guy. Prop step 2, tertiary, the break Br2, right? Oh, and then that's not on our table I currently have shown you, huh? I have to go find that one. Here it is. It's going to take 47 kcals per mole to break the R2 bond. Not much, huh? 46, I mean. And then I'm making a tertiary carbon to bromine bond. So tertiary carbon to bromine, I'm getting back 71. So it's 46 minus 71. What is that? 46 minus 71. Minus 25. So it turns out it's overall exothermic, and that step is exothermic, right? Make that blue since I was doing that in blue. All right, there we go. Finally, the last one here. Propagation step 2, primary. Which I should do in black ink. Huh? So oh, I didn't change the, I made a CBR there, huh, for minus 71. And here I'm making a CBR as well, but this one's going to be for a primary carbon to bromide. So primary carbon to bromide, 70, about the same. So it's going to be 24, huh? Cool. So it's exo as well. So they're pretty much the same, only like 1 kcal per mole difference. But actually this one should be relatively higher still, huh? A little bit higher because it's starting up higher and it's only going down 24. Yeah, I guess I'll fix that one. It doesn't really matter for us. We're going to find out shortly. The final product, we just need to know their exo, but we don't need to know like the big difference between them. Okay, and then our transition states here, activation energy, transition state 3, and then this one's the other one, activation energy, transition state 3. There we go, right? This is 3 for tertiary, and this one's 3 for primary. Okay. So I had a question about the rate determining step. The rate determining step, I haven't given enough information about it. This information, all these tables, this is all energy differences between reactants and products. So is that kinetic data or is that thermodynamic data? This is all thermodynamics, this stuff, thermodynamics. And the activation energy is kinetic. So we don't have enough information from these tables to get what's the rate determining step, but this is the rate determining step. I'm pretty sure we call this the rate determining step, even though it seems like this would be because you only put in energy. What's the Br2 bond strength? 46. It's probably, this is probably, you could this is the largest activation energy, but this is the rate determining step. It's complicated because you only need this to happen once, and then it starts that cycle, that radical cycle. So this is what actually determines the rate. So let's not worry too much about the rate determining step on this one. It's super complicated. Yeah, we can go over these more in office hours for sure. And we'll go over more now too. So the key thing about this is that this step here, propagation step 1, is the most important one. Here you can see it's faster to form this tertiary radical than the primary radical. The primary radical's got a higher activation energy. So what would you guess we make more of, the tertiary radical or the primary radical? We'll make more of the tertiary radical. And because we make more of the tertiary radical, we'll make more of the tertiary product. So we're going to find that this reaction produces almost all tertiary radical, very little of the primary product. We'll produce like, we'll calculate how much actually shortly, but we'll produce, this will be our major product, the tertiary product. All right, so the next thing I want to do with this diagram though is draw the transition states with the dotted lines. But before I do that, I want to introduce this thing called the Hammond postulate. And before I do Hammond postulate, I'll take a break. All right, well, what I did is I copied this, I screen captured this reaction coordinate diagram onto the next panel. And I want to use it to reference when I'm drawing transition states. But before I draw the transition states, I'm going to add another layer of complexity to our transition states. We're going to introduce the concept of the Hammond postulate. So the Hammond postulate is simply a guess at what the transition state looks like. Postulate is just a fancy word for guess. So the guess is actually kind of straightforward. The guess is, the postulate is, the transition state will look more like what it is closer in energy to. Products or the reactants or the products. Reactants, products. So for example, if I have a exothermic reaction, we'll predict using the Hammond postulates that the transition state looks more like the reactants. Let me draw an example for you real quick. I have to get my iPad going. So if you have an exothermic step like this, you have your activation energy here. Transition state will look more like products or reactants. I'm gonna type that out. What should it look more like, products or reactants? Reactants, because it's closer in energy to reactants. It's further in energy. Oh, come on, man. It's further in energy from the products. So that's what Hammond-Porsche says. Oh, that exothermic step, you're going to look more like reactants. A lot of people call it as a early transition state because it's looking more like reactants early on in the reaction. Okay, if I have an endothermic step, what should my transition state look more like, reactants or products? Good. Products. Looks more like products referred to as a late transition state. What did I just do? Make this blue, maybe make it a little different. All right. Because it's closer to the products. Okay, so let's use that concept to draw our transition states for this radical bromination of an alkane. So transition state 1, this one right here. Is that an exothermic step or an endothermic step? Endothermic. Is it closer in energy to the products or to the reactants? Looks more like the products. Closer in energy to the products. So when I draw it, I have to think about it. Oh, it starts off as a Br2 and it becomes a bromine radical. So I'm going to exaggerate this. It's going to look like this. It's going to have one bromine here, which is 3 lone pairs. And then the bond that's breaking, I show just dots, and I'll show it like really long, like it's almost fully broken in the form of the products. So I really exaggerated how long to make this. Very long. Almost fully broken. Okay, cool. Now let's try transition state 2. So I'm going to move this. Oh, I don't want to do that. Let me make this a little smaller, move it over here, get some more room. Okay, there we go. Now let's try transition state 2. Transition state 2, and we'll do the primary first. Oh, and I meant to do this. I was thinking about this during the break. Yeah, Alina, you can watch the recording later if it's not working for you now. Transition state 2. I'm sorry, transition state 2 primary. I want to make sure we understand. Let me do a quick review on this primary, secondary, tertiary stuff. Let's go like this. So when I look at this molecule, these two right here, what are they? Primary, secondary, tertiary? Yeah, this one's primary. What's this one here? Primary, secondary, tertiary? Tertiary, good. And then this one here? Primary, secondary, tertiary. Good, secondary. And then these ones. Primary. This one? Anybody know what that one is? Quaternary, yeah. Good job. Okay. Quick little review. I want to make sure you're not getting confused with that stuff. I'll just put this over here. Okay, so now back to our primary transition state. So in this step, let's look back at the mechanism too. This will really help. I'll draw it up here again. We have the hydrogen reacting with the bromine radical. Oh. And how are they meeting? Can you meet me halfway? Right, like that. So the HBr is forming, that bond is forming, and then the carbon-hydrogen bond is breaking. This step is endo or exo? Endo again, so it's going to look more like the products. In the products, we have a full-on HBr bond and a completely broken carbon-hydrogen bond. So let's try to draw that. So I'll draw it as like this, and then I draw dots to the hydrogen. This bond is just about fully broken, so I'm going to make it very long. And then the HBr bond is just about completely made, so I'll draw that one shorter. So this one's long, and this one's short. So that's how the Hammond postulate helps us. Has us draw the bonds breaking and forming at the correct length of what we predict them to be in the transition state. Okay, so moving on. Transition state, I'll do this one a different color. Transition state 2 again, but for the tertiary. Is this one exo or endo? It's also endo. It's right here, right? Still endo. Still went up. So if it's endo still, is it going to look more like products or reactants? Still like products. So easy enough. It's the same as the last one. This bond is almost completely broken, and this one's just about fully formed. So that one's long. This one's short. Getting it. Okay, last ones. What about the tertiary, the transition state 3 for the primary? Is that one exothermic or endothermic? We're talking about going from the carbon radical. Oh, you know what? I didn't even draw my thing right here. I made an error. Anybody notice that? I should have a Br radical for both of these products, huh? Br dot. Let me go back a page too. I should have it here as well. Where I copied it from. Okay. Minor error there, fixed. All right, so transition state 3 is exothermic. So now we got a little something different. It's not going to look like reactants, or not going to look like products. More reactant like early transition state. So let's draw that one up again to the curved arrow mechanism. That'll help a lot. So here we go. We've got, for this one, we'll have a carbon radical. So for this reaction, we have a primary carbon radical and a bromine reacting with it. And how do they meet? Can you meet me halfway? Like that. So we're going to be breaking the bromine bond, Br2 bond, and making a bromine to carbon bond. And it's going to look like reactants. So this bond we're making is just starting to form, and the bond we're breaking is just starting to break. So let's draw this up properly. So that's this bond between the carbon and bromine is just starting to form, so it's going to be long. And oh, and it's easy to lose your correct number of lone pairs on this one. We still have 3 lone pairs on this bromine in the middle here. And then the bond that's just starting to break is going to be short. So there we go. Short. And now hopefully the tertiary one will also make sense. So transition state 3 tertiary. We're just starting to form the bond to the bromine and the tertiary carbon. That bromine still has 3 lone pairs. And we're just starting to break the Br-Br bond. That a note. Okay, we use the Hammond postulate. I wonder if many of you are thinking, okay, who cares? Why are we making such a big deal about this? Well, we're going to use this theory to explain our reactivity we find experimentally, and then also make future predictions with it. So this is kind of a long story. We're midway through. It's going to make more sense as we go. Let me just pause though to see, is everything going okay so far? I don't know what you mean by our changes required, Santos. Okay, so let me talk to you about some, charges. I read it as changes. So good question, Santos. Santos asked, should I have like a delta plus, delta minus on these? Not on the radicals. No, not on this mechanism, because we start, for example, with, in this reaction, I started with a carbon with no charge, hydrogen's no charge, bromine's no charge, and their products, no charge as well. So we don't put delta pluses and minuses on these. And then Annalise said, for the last 2, shouldn't it go short long, since they're supposed to be more reactant-like? So on this, the last one, Annalise, think of it this way. When the alkane is all by, what did I do? Oh no, right here, huh? Yeah, when the carbon radical is all by itself, it's completely super far from the Br2. That's when they're reactants, right? Before they react, they're in different areas, far from each other. So this should be long. It should be very far from each other. I hope that helps. And if it's feeling a little fuzzy, totally understandable. We're going to practice this. You'll get good at it. All right, so now let me go into something else to help you with this. Let's look at reaction rates. here's some reaction data. So let's look at our example. In our example, we've been working on our bromination. We have this, what's called 2-methylpropane. And we react that with bromine and light. And we look at the tertiary product and the primary product, the products with just a single bromine, monobrominated products, and we make HBr as well. Okay, so what our rate data is telling us here is that a primary carbon, when it reacts with bromine, it reacts at a rate of 1. If you measure it experimentally, you can give it you can say, oh, it's reacting at some rate, I'll call it 1. And then the tertiary is reacting 1,700 times faster. So tertiary carbon to hydrogen reacts 1,700 times faster than the primary carbon to hydrogen. So that's our rate data. That's derived experimentally. Okay, so now what does this mean for us? Like, can we use this to predict reaction rates? Yeah, we're going to use this to predict reaction rates. I'm not reaction rate, reaction product ratios. Okay, so what do I mean by that? So first off, the product ratio, we're gonna factor in 2 things. This is how we're gonna do it. We'll consider 2 things, 2 tidings. First, the relative rate of reaction. That's the thing you see up there, the 1700. So like a primary is also tertiary. times. Then we'll also consider number of reactive hydrogens available. I sometimes refer to this as the statistical rate, probability. Collision. So for a reaction to occur, I want to make this smaller, we need to have a collision between the 2 molecules. So I spelled available wrong. The 2 atoms have to collide together in order for them to react. So let's check this out. So for the starting material here, we've got how many primary carbons? Nine primary hydrogens. I said carbons, I meant hydrogens. We got 3 primary carbons, but 9 primary hydrogens, right? And then in the middle here, we've got just 1 tertiary hydrogen. Okay, so there's, just in terms of collisions, there's 9 times more probability of colliding with a primary hydrogen than a tertiary, and maybe even more than that because the tertiary is more crowded on the inside. But let's not consider that. Let's just say the number of them. Yep, you were right, Ryan. I did say carbons, I meant hydrogens. Okay, so here's our relative, this is our predicted rate. Predicted, not rate, predicted product ratio. So for the primary and then for the tertiary. So for the primary, I've got 9 hydrogens times a relative rate of 1. For the tertiary, I have 1 hydrogen times a relative rate of 1700. So I'm expecting a 9 to 1700 ratio of the 2. So primary to tertiary products are going to be in a 9 to 1700 ratio. So what am I going to make the most of? Much more tertiary. And I can even calculate like an approximate yield. I could predict a yield from this. Let's go. I'm going to shrink this, give myself a little bit more room for this. So primary percent yield. I'm expecting 9 of those out of a total of 1700 plus 9 times 100. So let's see, I'll do that real quick on my calculator here. So I've got 9 divided by 1709 multiplied by 100. I'm expecting about 0.5% yield. So I'm thinking I'll get like 0.5% yield of the primary product. And then for my tertiary, that one's going to be 1700 tertiaries over 1700 plus 9 times 100. And I could just subtract 0.5. You know, it's going to be 99.5, but that's okay. Let's do it. 1700 divided by 1709 times 100, 99.5%. We say that this is our major product, the one we get the most of, and this is our minor product. Okay, so now we've got the relative rates. I'm going to do another example of that to make sure you get the feel for it, because I like these kind of questions. I'll ask them on the next exam, I'm pretty sure. Actually, let me see about our animations. I might have, if I'm remembering correctly, might have had honor students do this one last year. Let me go to my animations, maybe. Got some honors examples of this. So if you want to see my animations are here, but then the sheet 2 has the honor student ones. Let's see, they got equilibrium, SN2. No, I guess it didn't. Maybe this year that'll be a good second honors project. All right. Yeah. So actually, honor students who are listening, remind me that'll be a good one for you to work out. Boom. Okay, so let's do another example. We'll end with one more example. And then on Wednesday's lecture, you'll find out what's the deal with all this craziness. Why are we doing this? Maybe you're already starting to see it, but okay, let's do one. I'm going to do something with lots of products. Yeah. Actually, I'll just do the one I did earlier. Yes, that's pretty good. Let's say I brominate this. What kind of monobromo products can we get? When I say monobromo, I mean just adding one bromine. You can get occasionally more than one bromine added to the alkane. But we're just going to focus on the monobromo for now. Let's simplify things. So what do we got going here? We've got these two are equivalent, right? We got those products. We got some products here, here. Do we get any products here? Can we put a bromine there? No, no hydrogen there. But we can get this. This will be a different product here. So this is so no hydrogen. So, oh yeah, I'll introduce a couple, one more thing here. Regiochemistry. Regiochemistry, just the region of a molecule. Chemistry. So let's look at the regiochemistry here. So, okay. Just CRIB. Just. Okay. So I'm going to call this regio products made from these hydrogens as regioisomer 1 right here. Oh, why don't I type it? I should never handwrite. My handwriting's so bad. So these will be regioisomer 1. Regioisomer 1 and regioisomer 1 equals okay. So we got regioisomer 1, and then we're gonna call the next one regioisomer 2. And then regioisomer 3 here. And regioisomer 4 over here. Okay, so the easiest way to draw up all the different products for this is just to draw your reactant up a bunch of times without adding the bromines yet. Just like draw the reactant up like that. Like that's the exact same reactant I started with, right? So I'm going to use this for regioisomer 1. And then, so, okay, how do I do that? I'll just throw on a bromine here. Say, I'll do it in a different color so it's obvious that it's from regioisomer 1 there. And then regioisomer 2, draw up the same thing as before. And now regioisomer 2, it's bonded to this tertiary carbon here. And then I draw it up again. Regioisomer 3, it's a secondary bromide. Then regioisomer 4. Primary bromide over here on the right. And of course, we also make HBr. Okay, so this is duplicate regioisomer 1, regioisomer 2, regioisomer. Wait, I'm off on all these now. Regioisomer 3. This is 1. 1, 2, 3. Regioisomer 4. There we go. All right, now let's do some math on them. So let's look at the number of hydrogens that could react, and then also the relative rate. And then we'll multiply those to get our product ratio. Okay, so for the first one, to get this regioisomer 1 product, how many hydrogens could have reacted? Yes, 6 hydrogens. The 6 comes from the reactant side. There was 6 hydrogens that could react. All right, what about the number of hydrogens for regioisomer 2? Just 1 hydrogen, because it came from this tertiary position there. Regioisomer 3, how many hydrogens? 2 hydrogens. Regioisomer 4. Nine hydrogens. Cool. And now relative rates. We know the relative rates from the primary and the tertiary. The primary was 1, tertiary was 1700, but we don't know secondary, but maybe I got that back here. Do I? Yes, I do. Let me copy this. Put it on this page. Yep. So we got our for primary bromide, we have primary, secondary, tertiary. It's 80 for secondary. So the relative rate for primary is 1. For tertiary, it's 1700. Secondary, it's 80. For primary, it's 1. So now when I multiply these 6 hydrogens times 1, it equals 6 for this one. 1 hydrogen times 1700. It equals 1700. And then 2 hydrogens times 80, that one's 160. And then 9 hydrogens times 1 is just 1. All right, so which product do I get the most of? Regioisomer 2, it's the major product. And then the second most major. Second most major, 160. And then this one, no, what did I wrote 9 here. 9 didn't come out. I guess this is our most minor, even though it's pretty much the same as the other one. There's basically none of these main. And then we could easily do a percent yield. Let's see, what's the total here? 1,700 plus 160 plus 9 plus 6, 1,875. So 6 divided by 1,875 equals that times 100. So it's like 0.3% yield of that one. Then the 1,700 divided by 1,875 is that times 100. 91%. 160. .5%. And finally, 9 divided by 1,875 times 0.5%. So you can see we're basically making tertiary products. Very little of the other ones, a little bit of secondary, but the primaries, almost nothing. And we'll use the Hammond postulate next lecture to try to rationale why that is.